Hi. Okay, so I'm going to go ahead and just teach today's lesson, which was intermolecular forces. So let me go ahead and write today's intermolecular forces. And I want to start by just dissecting that name, intermolecular. Inter, a lot of times we think of within, but that is incorrect. If I really take apart that word, inter, I might think of international calling. That means calling between countries, or an international flight is a flight between countries. So it's usually outside of one's own country. So intermolecular forces are the forces outside of the molecule. There are forces outside of the molecule. So in order to talk about intermolecular forces, I first want to talk about intramolecular forces. So let's go ahead and start with that. Intramolecular forces, intramolecular. And a lot of times we use these words forces and the word bonds interchangeably, and truth be told, that is incorrect. So these intramolecular, these I might call bonds. These are true bonds. And we've learned a couple of intramolecular bonds. We have learned covalent bonds. That's a type of bond, a covalent bond. Covalent bond is between two nonmetals. Okay. And what's another type of bond that we've learned? We've learned about an ionic. And that's between a metal and a nonmetal. Okay, and we haven't learned yet about the third type, but there is a third type, and that's going to be called a metallic. A metallic bond is between one or more metal atoms. Okay. So again, we have covalent, ionic, and metallic. These are called intramolecular bonds or intramolecular forces, but I like calling them bonds because they're true bonds. Again, a covalent bond is between two nonmetals. An example of this would be water. Water is held together by covalent bonds, which is an intramolecular bond. An example of an ionic bond is, let's say, sodium chloride, NaCl. And again, that's held together because my Na gave up its electron to, sorry, I'm struggling over here, to chlorine, which was missing an electron, causing a positively charged cation and a negatively charged anion. Okay. And then a metallic bond, we're going to talk a lot more about that in the coming days here. But what that is it's a metal atom. And so for this example, I'm just going to say copper. And it's a whole bunch of copper atoms. And again, we're going to learn more about it, but all we need to know is a whole bunch of copper atoms with electrons flowing in between, okay? So just these atoms with electrons free flowing. Okay, these intramolecular bonds are held together by electrostatic attraction. All of them are held together by electrostatic attraction. And if we're going to remember in our notes, electrostatic attraction is just simply the attraction between positive and negative charges. Okay, so where is the electrostatic attraction in a covalent bond? Well, in a covalent bond, it's a little bit harder to see. The positive would be in a proton, and the negatives would be electrons. So the proton within the nucleus is being attracted to the electrons outside the nucleus, and that's going to hold together these molecules in a covalent bond. But how about an ionic? Where are my positive and negative charges? Well, I have a true charge on my ion. My cation has a true positive charge. My anion has a true negative charge. So the charges on my ions are what hold my ionic bond together. And again, this is the strongest. This one right here has the highest electrostatic attraction. Super strong bond. And metallic is a lot like covalent in the sense that it's just between the protons and the nucleus and these free-flowing electrons. So again, ionic is the highest because there's true charges, true opposite charges being pulled together, whereas the others are just between the protons that are in the nucleus and the electrons that are outside the nucleus. And there's an attraction there. But they're all being held together through electrostatic attraction. Okay, now that we've talked about intramolecular forces, I'm going to go ahead and draw that again. So I'm going to write, I'll write bonds, and then I'm going to write ionic, covalent, and it could be in any order, it doesn't matter, metallic. Now, ionic tend to be solids at room temperature. They tend to be solids at room temperature. And metals a lot of times are solid at room temperature. But what about, please tell me this is still recording. Okay. What about covalent? Are covalent bonds, can they be solids? Because a lot of times when we think about covalent bonds, they're usually gases. Like the air we breathe, if you take a deep breath in, what we're breathing in is a gas. And yet we can cool down these gases to become liquids and to become solids. How do we do that? We might be like, oh, we cool it down. Yeah, we are cooling it down. But there has to be something between those covalent bonds that are going to stick them together. Okay, and so that's what we're going to be looking at today. We're going to be saying, what is going to hold my covalent bonds together, or those covalent molecules together? So what we're looking at are intermolecular forces. And what that is an example, is like here's a water molecule, and here's a water molecule. There has to be some sort of attraction between one molecule and the other molecule that holds these molecules together as a solid. Otherwise, it wouldn't be able to form. Okay, so there has to be some sort of attraction. And that's what we're going to be talking about, are these types of intermolecular forces, and we're going to call them a force because they're much weaker than bonds. Those bonds, as ionic, covalent, metallics, they tend to be very strong, whereas these intermolecular forces, they are weaker. Okay, they are weaker. They're a physical change, whereas the bonding is a chemical change. I'm going to say that again. The bonds, ionic, covalent, metallic, those are chemical changes, whereas these intermolecular forces, they are physical changes. They are between the molecules. Okay, there are three types of intermolecular forces. The first one I want to talk about is a dipole-dipole. A dipole-dipole happens anytime, well, let's take apart the word dipole. Di means two, pole, it's like polar. So I told you guys that you can't forget any information in this class, and true enough, we have to remember what polar means. Polar means that one bully is pulling stronger on the electrons than another bully. So for example, if I drew out fluorine, which is a diatomic molecule, if I drew this out, I see that fluorine is playing tug-of-war with fluorine. Who's going to win? Well, neither. They're equal. It's two fluorines. So this one is non-polar. But what if I did like HCl? I drew that one out. HCl, I see here, chlorine is a much bigger bully than hydrogen. And so I know that chlorine is pulling those electrons towards itself. And I know that electrons are negative. So that creates a partially negative side to my molecule and a partially positive side to my molecule. So what I have created is a pole, kind of like a magnet, a north pole and a south pole. Well, I have now a negative side or a partially negative side and a partially positive side. That's what that symbol is right there. Delta means partially. Because it's not a full charge. It's not a true charge. It's just partially negative. It's partially positive. And so we have this pole, and you're going to notice that we have two poles, a negative pole and a positive pole. So therefore, we have two poles called a dipole. So, oops, that's awkward. What the heck? Stop. Okay, I've never had that happen before. It's like automatically going back as soon as I lift up my pen. Okay. So why do I say dipole, dipole? Well, it's because we have more than one molecule in any sort of gas, right? So here are two molecules, and of course, the chlorine is a bully. The hydrogen is having its electrons stripped away from it, okay? And so let me choose a different color. This delta negative chlorine is going to be attracted to that delta positive hydrogen. And so the pole of one molecule is going to be attracted to the pole of another molecule. So how do I know if there's a dipole-dipole interaction between two molecules? I'm going to know that there is a dipole-dipole interaction because the molecule is polar. Okay. Now, the next type of intermolecular force that we talked about that's going to be between the molecules, again, that's what we're talking about, is between the molecules. That is going to be a hydrogen bond. Now, a hydrogen bond is going to happen. It's an extreme type of dipole-dipole. It's still dipole-dipole. It's just like it's so much stronger that we actually give it its own name. It's actually going to be when a hydrogen is attached to a nitrogen, oxygen, or fluorine. Okay, so for example here, let's take a look. Actually, I already have water drawn. Let's go ahead and take a look at it. Let me erase all of this. Hopefully it's gone enough because it's going to drive me nuts. Okay, so I'm going to take a look at my water here, and I'm going to say, is there a positive side and is there a negative side? Well, I know that oxygen's a bigger bully, so I'm going to put a delta negative there. And poor hydrogen is just having its electrons ripped away. So this side is more positive, and the oxygen is more negative. Again, this one is negative, and this one's positive. And again, we've created this two poles, but what's happened is these poles are actually more like they're a stronger dipole. They're just a stronger dipole because oxygen, nitrogen, and fluorine, they're like the biggest bullies on the playground. I mean, yeah, that chlorine was kind of a bully and it created a dipole, but they're not as big of bullies as nitrogen, oxygen, and fluorine. So that creates even a stronger dipole, so much so that we give it its own name called a hydrogen bond. Now, you want to be careful because sometimes you might look at a formula like CH2O and say, oh, the hydrogen's going to be bonded to the oxygen, so that's going to have a hydrogen bond. Realistically, in order for us to know if it's going to have a hydrogen bond, we're going to have to draw it. So carbon is always my central atom. I'm going to remember that carbon has 4 valence electrons. Hydrogen has 1 valence electron, and there's 2 of them. And then oxygen has 6 valence electrons. And so 6 plus 4 is 10, plus 2 is 12. So when I draw this, I believe 2, 4, 6, 8, 10, 12. Yeah. When I draw this just should be what I get right now. And is the hydrogen actually attached to the oxygen? It has to be attached to the oxygen. It's not. The hydrogens are attached to carbon, so therefore this is not a hydrogen bond. This would only be a dipole-dipole. Now it can, like water, can be dipole-dipole and hydrogen bond. So you have to look and say, like, what intermolecular forces are holding these molecules or holding a bunch of molecules together, like a whole bunch of waters? What's holding the bunch of waters together? It could be hydrogen bonds and dipoles, or it could be just dipole. And we're not going to learn about the third one until tomorrow. So that's where we ended. I hope you're having a decent day. Bye.